Let me show you how to be a good Bayesian.
In this episode, I am joined by Sam Witty, founder of Cerberus AI. Sam is the driving force behind ChiRho, an open source framework that extends Pyro with causal capabilities, giving scientists and engineers a way to run counterfactuals, analyze path-specific effects, and build hybrid models that combine machine learning with domain knowledge. We talk about the challenges of translating causal questions for clients, the importance of Bayesian thinking for scrutinizing assumptions, and the real-world impact of causal probabilistic programming, from sustainable energy to preemptive health. This is Learning Bayesian Statistics, recorded July 31st, 2025.
Let me show you how to be a good Bayesian. Change your predictions after taking information in. And if you're thinking I'll be less than amazing, let's adjust those expectations. What's a Bayesian? It's someone who cares about evidence.
Welcome to Learning Bayesian Statistics, a podcast about Bayesian inference, the methods, the projects, and the people who make it possible. I'm your host, Alex Andorra. You can follow me on Twitter at Alex_Andorra, like the country. For any info about the show, learnbayesstats.com is la place to be. Show notes, becoming a corporate sponsor, unlocking Bayesian merch, supporting the show on Patreon, everything is in there. That's learnbayesstats.com. If you're interested in one-on-one mentorship, online courses, or statistical consulting, feel free to reach out and book a call at topmate.io/Alex_Andorra. See you around, folks, and best Bayesian wishes to you all. And if today's discussion sparked ideas for your business, well, our team at PineC Labs can help bring them to life. Check us out at pinec-labs.com. Hello, my dear Bayesians. Big news, I am considering running a 6-week, more or less, live cohort of my advanced Bayesian regression course from Intuitive Bayes that I wrote with the brilliant Ravin Kumar and Tommy Capreto. Think weekly live sessions, projects, office hours, community. So if you are into practical Bayes and want to see how it's done in the wild, in practice, and want to learn that, well, if that sounds interesting to you, feel free to answer the short Google form in the show notes to help me scope demand and logistics, and of course, also to get the early bird access and discount. Thank you so much for your help and for being such a good Bayesian. Sam Witty, welcome to Learning Bayesian Statistics.
Thank you. Glad to be here.
Yeah, I am super excited to have you on the show because, well, you're doing things I am very interested in, especially these days where I'm ramping up my causal inference intersecting with generative AI modeling skills. I discovered your work through Robert Ness's episode with us and also his great book, Causal AI, where he uses ChiRho, and you are, of course, one of the developers of this great package. So we'll talk about all that today. And if you have some stuff, by the way, you want to share on your screen, demo stuff live, or else let me know. You can share your screen, and that will be then on the YouTube channel for people who want to follow along. But first, as usual, we're going to dive into your origin story, Sam. So, yeah, what are you doing nowadays, and how did you end up working on that?
So right now I'm the founder and principal consultant at a company I founded called Cerberus AI. We do consulting on probabilistic and causal AI, mostly for engineering and scientific clients. I'll talk a little later about why I think that's a really sweet spot for this technology right now. But at a high level, it's a boutique consultancy where I sit very closely with clients and help them kind of bridge the gap between what I call mechanistic and kind of data-driven modeling workflows. So the story that got me there, in undergrad, I was a mechanical engineer. I actually don't have a undergrad computer science or statistics background. And I came into this world sort of by accident. I was a working mechanical engineer. I worked for a small consulting firm that was doing energy efficiency consulting. Actually, a fun aside, I was doing causal inference without knowing it was causal inference. We were evaluating public policy programs that give money for energy efficiency projects, and they wanted to know what the causal impact of those programs were. So at that job, I spent a lot of time doing kind of engineering first modeling, building models of fluid dynamics or heat transfer, these sorts of things. But I felt like very quickly that wasn't really able to keep up with the data we would gather in the real world. So that naturally brought me to statistics and machine learning, which at the same time felt like I had to throw away all of the mechanistic knowledge I had learned in engineering school. So with that kind of tension in mind, I went to grad school, studied a bunch of things we'll talk about today. And now this consulting work is kind of coming full circle. I'm trying to bridge the world between engineering first, modeling where you think hard about the physics, think hard about the mechanisms in the world, and the kind of probabilistic and causal AI that's made a lot of technical progress in the last several years.
Yeah, definitely. And I really like how you're blending all these different experiences into what you're doing today. And I'm actually also wondering, you did your PhD at UMass Amherst, you did a visiting at MIT, and if I understood correctly, both of those revolved around some kind of probabilistic programming. So was there a particular moment that, turned that academic work into a career focus, where you knew you wanted to focus on that for at least the coming years because you thought it was really interesting?
Yeah, I've always been academically minded. For any of your listeners who went to engineering school, you'll remember a common phrase that professors make, which is, I'm sorry for all the math, but we'll get to the cool stuff soon. And that was never me. I liked the math. So, doing a PhD was a pretty natural progression for me. But at the same time, I think that the career focus has been kind of driven by my past engineering experience. And then I see the computer science academic background as developing the schools to kind of meet that end. Whereas other people might have started with a set of tools and then later developed those tools into application areas for their career.
Okay, I see. Yeah, that's interesting. I didn't know the engineering professors were like, okay, let's get the math out of the way and then focus on the cool stuff.
Yeah, it's often a lot of car nerds. They want to build engines or design circuits, and some, not all, certainly not all engineers see math as an impediment to doing the cool physical things they want to do.
Yeah.
It's obviously it's a broad sweeping statement. Many engineers are as
for sure.
as math nerdy as I am.
Right. Yeah. No, that reminds me, of the TV series Big Bang Theory, where of course Howard is the only member of the team who is an engineer and always get teased by Sheldon because first he doesn't have a PhD and second he's an engineer. So that made me think about that. And which is of course not true. The proof is that you are on this podcast, which is very academic. Something also I was interested in when preparing for your episode was that on your homepage, that's in the show notes, by the way, folks, you say that you help teams combine mechanistic knowledge with data-driven machine learning. From where you're coming from and the answers you just gave, I really understand now why you're saying that on your website. But I'm also wondering when you first realized that marriage was a missing ingredient for many hard tech problems.
Yeah, it's a great question. So, one of the core things about engineering models is that you can extrapolate with them. right? For a lot of models, they're derived from very simple concepts, right? You might look at Newton's laws, for example, and a lot of engineering modeling is about seeing the natural consequences of those very simple laws. So, for example, you can derive things about objects colliding or rotation, leverage, inertia, conservation of energy, all from these kind of basic fundamental laws of the world. And for the most part, those laws generalize, right? If I imagine a bridge that I've never built before, using these kind of mechanistic laws, I can be pretty confident that if I've been careful about the math, that the bridge is going to work the way I would expect it to work. Now, there are some caveats, of course. Some materials behave in somewhat unsuspecting ways, but with a large asterisk, that is generally true. Like, we expect engineering kind of mechanistic models first to generalize to unforeseen worlds. And that matters, right? People want to build systems. They want to make predictions outside of the realm of the data that they've gathered. They want to be able to explain what would have happened had something been different to inform policy decisions. So people care about causality, but they also care about learning from data, right? Our knowledge of the world is fundamentally incomplete. And if all you ever did was sat down, wrote down a model by hand, and then probed it for its logical implications, the model would likely not represent the world very well. It's just too complicated to try to model everything by hand. I think past waves of AI research have kind of taught us this. So the key point is that we should learn something from those mechanistic models of the world, try to get some of that extrapolative capabilities, but not lose all of the kind of data-based machine learning approaches or statistical approaches that have seen a lot of progress. And I happen to think that probabilistic programming, and in particular causal probabilistic programming, is an extremely natural way to kind of bridge these two worlds.
Yeah, actually, that's a good segue into trying and defining all that. Can you define those terms? How do you differentiate them, and why do you think that causal probabilistic programming has? Why do you have such hope for it to be able to bridge that gap?
Yeah. So when you say define those terms, you mean causal probabilistic programming?
Yes, exactly. And
yeah, great.
The difference with the classic data-driven machine learning.
Sure. So it's worth zooming out a little bit. Maybe we could start by talking about what is probabilistic programming before adding the causal part. So probabilistic programming, in its most simplest form, is just programs with randomness. You can think of it essentially as writing simulation models that have special syntax for denoting random variables and distributions. Now that's kind of a simplified representation because it doesn't tell you what they do, right? And what you do with probabilistic programs is to automate or semi-automate a process known as inference, which is about manipulating distributions to answer questions. So some manipulations look like marginalization. What would happen if I were to sort of average over a particular variable in my model, or conditioning, where you hold some variable fixed at some data and then update your distribution over all of the other random variables. And these reasoning operations, these core reasoning operations of marginalization and conditioning, can be very computationally challenging. So probabilistic programming languages often come with a set of inference algorithms that either exactly or approximately solve those reasoning steps. So that's purely probabilistic. It's like, imagine coin flips or dice rolls or things like that. At this point, no causality is kind of imbued in these systems. You can ask them about what is likely to occur when other events happen. But causal probabilistic programs give this kind of idea of taking action or intervention in your system. And they let you answer questions like, how would my distributions change if I were to hit my system with a hammer in some way, if I were to intervene? And how would those changing distributions propagate into the things I care about? So causal probabilistic programming systems are systems that, similar to how probabilistic programming systems help to automate probabilistic reasoning, causal probabilistic programming systems like ChiRho help to automate causal reasoning, asking these kind of what-if questions that, as I said, many scientists and engineers and policymakers care a lot about.
Yeah. And I'm actually super grateful that you developed that whole package, because it's definitely something I'm gonna use a lot, and mainly because it's built on top of a probabilistic programming package, which is amazing, because like you get to keep all the goodies of Bayesian models, basically, where you have already the generative structure and you can do forward and backward sampling. But then you add the causal structure, the ability to intervene on your causal graph, to do counterfactuals and stuff like that. So I find this is extremely helpful. And actually, that's a good point now for us to turn and talk about ChiRho in particular. I'm curious, first, what design principles of ChiRho you are particularly happy with, and also why was Pyro the right backend in your mind to do that?
Yeah. So maybe I explained what causal probabilistic programming was in general, but maybe I could just take a few minutes to explain what ChiRho is.
That's
more
true.
specifically.
Yeah. I forgot my own question. Thanks for doing my job,
great.
Sam.
That's okay. You can do my job later too if you want.
No, that's way harder. I think I prefer it like that.
Well, we'll see. So ChiRho is a causal extension to the Pyro probabilistic programming language, which is built on top of PyTorch. So Pyro was one of the earlier probabilistic programming languages to really take deep learning and kind of differential programming as kind of a core building block. So Pyro is built on top of PyTorch. Pyro programs are essentially collections of PyTorch operations with special, as I said, special syntax for defining random variables. So ChiRho, in a certain sense, is just a wrapper around Pyro programs. You write your probabilistic causal models as you would any other probabilistic program. It's just that when you're writing it, you have to kind of imbue it with a little bit more meaning than you would an ordinary probabilistic program. You're making a kind of implicit assertion that the order of variables that you write represents like the causal ordering of things unfolding in the world. Whereas this is not something you need to do explicitly if all you care about is estimating marginal and conditional probabilities, as in Pyro. So with that kind of conceptual difference, ChiRho provides two main pieces of functionality above what Pyro does. One is, as we said, an intervention operator. So this takes a probabilistic program and transforms it where some intervention has been applied. You can think of this intervention like forcing some variable in your system to take a particular value or to be generated by some function that is not the normal mechanisms in your probabilistic program. And the other thing that ChiRho does, which as far as I can tell, no other systems yet support, is to provide sort of bookkeeping for managing what we call counterfactual worlds. And this is important because lots of really rich causal questions involve combinations of outputs from different worlds with different interventions applied that are interacting with each other. And without this kind of support in ChiRho, that kind of reasoning is really, really difficult. I can give an example of that if you'd like. Okay, so a common thing you might want to do with your model is understand what are called path-specific effects. So for those familiar with the jargon, this is called mediation analysis. And the idea is that if I have a large and complicated model, I might want to isolate the effect of one variable on another variable only through a particular pathway. I don't want to know the total effect of, treatment on outcome. I only want to know the effect mediated through something I particularly care about.
Yeah, so that'd be like,
yeah.
maybe to give an example to people, it's like if you have a confounder, so common cause of the treatment and the outcome, you obviously have two causal path here from the treatment to the outcome, but you only have one direct path, which is the one.
So this is actually a subtlety.
Treatment to the outcome.
That the confounding relationship. So for those who are unfamiliar, confounding. I never know how far to back up the jargon, but I'll just go far up. So confounding is when you have a variable that influences both the thing you're interested in intervening on and the thing you're interested in measuring the outcome. So in this setting, actually, confounding is not the issue. The issue is that between my treatment and my outcome, there are many different paths, all pointing the same direction.
Okay, so that'd be more like if you had a direct path and then a path that's mediated?
Yeah, exactly.
Okay.
Exactly.
Yeah. Okay.
And you want to be able to isolate how much of the total effect is going through each of these different paths.
Okay.
So one way to codify this is using what are called nested counterfactuals. So you can reframe this question of what is the path-specific effect of treatment on outcome as, let me make sure I get this right. What would the outcome be if I intervened on treatment and intervened on the mediator to be what it would have been had I not intervened on treatment?
Right. Yeah.
So that long convoluted sentence involves intervening in two different ways in two different places with values sampled from a different counterfactual world and kind of interweaving with each other. That sentence is very difficult to codify unless you have the counterfactual worlds that ChiRho provides. And with ChiRho, it's 4 lines of code. And we actually have some tutorials that show exactly how to do that. If you go, you'll see a mediation analysis tutorial on the docs page.
Yeah, and the docs page is in the show notes. I highly encourage people to check it out.
Yeah. So it's like mediation analysis is one example, but it turns out that these manipulating counterfactual worlds is necessary for answering other questions, like the ambiguous question, like why did something happen? It turns out to represent that, you need to do a search over possible counterfactual worlds and optimize that search for outcomes where the thing you're trying to explain is likely to happen and some other conditions are unlikely to happen. So doing that kind of search over counterfactual worlds is, again, not easy. That's kind of stretching ChiRho as far as it can go. But at least it can be mechanized in ChiRho. And it's very difficult otherwise without these utilities.
Yeah, I can I can attest to that. And that's why the work you're doing on ChiRho is very important to help practitioners focus on what is actually the most interesting things to them and the most important and the thing that is actually customized to their use case. Whereas what ChiRho is doing is trying and abstracting away the math, which is basically the thing that's generalizable. So like in all cases, you're going to need do calculus. You're going to need to analyze your counterfactual graphs. And so ChiRho is doing that for you, so then you can just focus on, okay, what are the DAGs I'm focused on? What are the counterfactual queries I'm actually after? So I think this is absolutely awesome for people.
Hello, Media Bayesians. Just a short break to let you know of a very exciting opportunity I have for you. Learning Bayesian statistics friend of the show, Robert Osasu MS, has just opened a new cohort of his Causal AI online course. And you know what? I personally will be part of this cohort. So if you want to come learn with me, make sure to enroll at the link in the show notes by Sunday, September 21st. Of course, you have a 15% discount if you're a patron of the show. I already shared the magic code with you on Discord and Patreon. In this course, we're going to see how to merge the power of deep learning, causal inference, and probabilistic programming all in the same models. And honestly, as a lifelong learner, I am beyond excited to add these causal arrows to my statistical quiver. So if you need more details, you can listen to Robert's latest appearance on the show, which is episode 137. You can check out the workshops page in the show notes, or you can just launch a discussion on Discord if you're a patron. Hope to see you in the workshop, folks. And well, I hope that I will learn with you and with Robert. And now, let's get back to my interview with Sam Witty.
So one point of clarification there, because it's a little subtle, is that ChiRho doesn't actually use the do calculus. So for
interesting, I thought you guys were. So yeah, how do you do that?
Yeah, I can explain. So
yeah.
So the do calculus is a set of symbolic rules developed by Pearl and students several years ago that translate causal questions into probabilistic questions for what are called non-parametric structural causal models. So the idea is that if all I have is a graph, which denotes the structure of causal relationships between my variables, then the do calculus gives me a sound and complete algorithm for translating that into probabilistic expressions that I can estimate from data. One of the limitations of the do calculus, it's a great tool, and I think the symbolic approaches are awesome. I see what we do in ChiRho as supplementary. One of the limitations of the do calculus is there's a key word I said in the definition, which is non-parametric. And a lot of the times, the models we write about the world include parametric assumptions that actually make it really much easier to do causal inference generally. So an example of this is if you're familiar with regression discontinuity designs, this is what's called a quasi-experimental design, where you have observational data where you have a continuous covariate. So for example, a classic example is the test scores a student get on an exam. And you have a treatment, which is, in this example, whether they are admitted into the next grade or not, or whether they're held back. And then an outcome, which is their education outcomes in the long term. So a regression discontinuity design takes advantage of the fact that we know that there's a fixed threshold in this test score, where if you're to the left of this threshold, you get held back a grade. And if you are to the right of this threshold, you advance to the next grade. And a key conclusion of this is that you can look at individuals who are very, very close to that threshold on the left and the right, and kind of intuit that because they have such similar values of test scores, which may confound the relationship between whether they get held back or and whether they how their education outcomes are, you can assume that they're basically the same because they're infinitesimally close to each other, but they have this kind of differentiated treatment. So it turns out that if you're willing to make these parametric assumptions about smoothness of the functions, or even just this discontinuity existing at all, you can estimate what's called the conditional average treatment effect arbitrarily close to that discontinuity. That kind of assumption is really easy to write as a program. You can't, as far as I know, write it directly as a graphical model. Like the structure of the variables influencing each other doesn't tell you enough to encode that. Okay, so we use a different way of thinking about causal inference.
Yeah.
which I call in my thesis Bayesian structural causal inference. So the idea, actually, is it okay if I share some figures?
Yeah, for sure. That's gonna be yeah, and actually that's where so people listening, you might wanna switch to the YouTube channel, and you'll have the chapters in the description, so you can jump right into that moment in the episode.
Okay, so this is a kind of a cartoonish view of what a structural causal model does in what we call the factual world. So you can think of this space on the left as the sort of space of all the causal models in the world that you're considering, and the space on the right is the data that you would observe. So here you can see it's, again, kind of cartoonish, but you can imagine a single structural causal model inducing a distribution over data. So being good Bayesians, we can put probability distributions on these things, and again, quite cartoonish. But now, if you imagine a distribution over structural causal models, that induces a much broader distribution over the data you would see.
Yeah, that makes sense. Yeah.
Great. So then, again, kind of, hopefully this is all very intuitive. If you start with a distribution over structural causal models and then you observe factual data, you can propagate, you can condition on that data and propagate that into a posterior distribution over these structural causal models. And so far, this is nothing but ordinary Bayesian inference. There's really nothing new here. But interesting things happen when you start to add these intervention transformations. So you can think of an intervention as a kind of function between models. It takes a structural causal model and turns it into a different structural causal model, which, as you can see here, is kind of in a different point in structural causal model space. So the original structural causal model induces a distribution over data, and the intervened structural causal model induces a different distribution over data.
Right.
And you can construct what we call a causal query, which is some function of your distribution over data and counterfactual data. So this might be like the average difference between outcomes under intervention and under your original world. So again, the story is similar. If we induce a distribution over structural causal models, that propagates to a distribution over intervened structural causal models, which then propagate to distributions over factual data and counterfactual data, and then a distribution over the causal query. And it turns out that if you've set up these interventions in a certain way, I mean, essentially you just need to preserve measurability, then the whole thing can just be treated as one big probabilistic inference problem. So now, rather than having just a joint distribution over models and data, you have a joint distribution over models, data, intervened models, counterfactual data, and counterfactual queries. But that's just a joint distribution. And the machinery of probabilistic modeling and inference tells us how we can manipulate these joint distributions and get posterior distributions over all the things we care about. So your factual data propagates to the posterior over structural causal models, which then gives you a push-forward distribution onto intervened structural causal models, which then pushes forward into a distribution over counterfactual data. And then you get a sort of posterior distribution over answers to your causal query.
Yeah, this is great.
Yeah. So this is
Thanks for sharing
this idea of just like taking causal models and turning them into probabilistic models is not unique to ChiRho or my thesis. But I think in ChiRho we really codified this and made it very explicit. So one way of thinking about what ChiRho is doing is it's automating this edge here, intervening from a structural causal model to a different structural causal model. And it's automating constructing all these different parallel worlds that construct this big joint distribution over different worlds. But then once you have that, like I said, it's just probability once you get to this space. And then you can use all of Pyro's existing inference tools to approximate inference however you'd like.
Yeah. Yeah, this is amazing. Thanks a lot for sharing that.
Yeah, no problem.
Makes me want to try this right now. I need a use case. Yeah.
Spin up a ripple. Let's go.
Yeah. Man, yeah. Like, I'm gonna use that very soon. I have some ideas of projects I can apply that to. And that sounds, yeah, I think it's super interesting, and I do think, it's filling a need we have right now with the generative AI, and making sure we can harness its power in a more structured way. So it's not going to be helpful for every problems, but I'm guessing there is a lot of problems for which is going to be extremely helpful.
Yeah.
And that was great.
I realized
Go ahead.
I kind of skipped your actual question. You asked me about ChiRho's design, and I talked about what ChiRho is.
Yeah, that's fine. I was gonna ask you again that.
Okay.
And then maybe we can walk through a duoperator concrete example after that. But yeah, first, if you can come back to the designing of ChiRho.
Yeah.
And yeah, I think you answered the Pyro part, why you based it on Pyro, but mainly the main philosophy, if you want, the Zen of ChiRho, let's say.
Yeah. So it's worth saying the caveat, which is that one reason we designed it off of Pyro is because Eli Bingham, who was another core developer of ChiRho, arguably, the lead developer and architect, was also a core developer of the Pyro probabilistic programming language. So there's a certain practical element of just familiarity.
That helps.
Yeah, for sure. It helps, certainly. At the same time, I think there are some interesting things about Pyro's design that made it easy to build off of. So the main goal with ChiRho was to make the causal probabilistic programming language modular and extensible. So modular meaning that it could be decomposed into kind of atomic parts that can be combined at will to solve all sorts of different problems. So that means users can write models in a modular fashion and combine it with many different questions. They can take many different questions and reduce them to probabilistic inference, and then have modular choices about what probabilistic inference algorithms they use. So that combination of like freely being able to mix and match models, questions, and algorithms gives you this like combinatorial explosion of choices as a modeler. And they're choices you can kind of enumerate pretty quickly, right? Moving from an average treatment effect to a conditional average treatment effect is, again, just a few lines of code. Going from a conditional average treatment effect to mediation analysis is another few lines of code. Modeling non-compliance in your treatment assignment is another single line of code. You just add a distribution to your intervened treatment assignment. And because this is all just code, all the kind of composability you would normally get from software follows in ChiRho programs as well. You're not really constrained to just thinking of causal inference questions as a kind of catalog of different things to choose from. It really is a programming experience, which we were really intentional about. The other thing we were trying to achieve, which I think we have, is to make ChiRho extensible. So it was pretty clear when first building ChiRho that we weren't going to build in all of the capabilities that we wanted from the get-go. The literature is too large and complicated. Research continues and progresses the field. So we wanted to design it in a way that as new research was developed, it could be tightly integrated into ChiRho without kind of uprooting the whole system. So there are two ways that we've seen that happen already, which I could nerd out about for a very long time, but maybe we can delay for later. One is extending ChiRho's modeling language to support continuous time dynamical systems. And and we have a paper that's currently in review and will be coming out soon, kind of describing all the math of what's going on there.
So, yeah,
yeah.
what do you mean by that? What's the problem right now, and what would that solve?
Yeah, so the problem is that by default, intervention semantics for probabilistic programs don't tell you how to deal with continuous time. And they don't tell you how to deal with models written as differential equations.
So that means, does that mean when you have, so for instance, time series, or is it also a problem if you have continuous variables? So like, do you mean that your outcome and treatment always have to be binary, or can they be continuous?
No. Variables can be continuous in ChiRho. That's really no problem.
Okay.
Defining an intervention on a continuous variable is just as easy as defining an intervention on a binary variable.
Right.
Estimating can be harder, but that's kind of a separate question. What I mean is that if you have a time series model, like a differential equation, that describes the behavior of the system at every point in continuous time, a key challenge is that when you're simulating this system, you don't actually visit every point in time. You would approximate this continuous time system with a collection of finite time points. And if you did the naive thing of just applying an intervention to any of those finite time points, you might miss the time where you want to apply an intervention. And sometimes you might want to have an intervention where you don't know in advance when it's going to occur. So for example, if you're modeling a control system that turns on an HVAC controller when the temperature of some room gets above some threshold, but you kind of need to like wait until you see what the temperature of the room is before you can decide when to intervene. And that kind of representation of an intervention just wasn't covered by the existing literature.
Okay. Yeah. That
So,
sounds harder. That definitely sounds harder.
It's harder, but at the same time, one of the really cool things about ChiRho is if you define what it means to intervene in such a system, which is work. I mean, there's a fair amount of math to make sure that works out correctly. But once you've done that work, you get all of the other thing ChiRho provides to you for free. So now all of a sudden you can ask mediation analysis questions of differential equations models. You can ask attribution questions. You can ask about probability of necessity or probability of sufficiency. And this works because, like I said, ChiRho is modular. We have this abstract notion of an intervention. We define what that means on any given modeling system. And then we have queries that combine these abstract interventions in a way that's, so the query model agnostic, even though it's implemented concretely on any given model. So that's very exciting. I happen to like those kind of models, but also I just think it's a really interesting demonstration of kind of how far we might be able to take causal reasoning into different modeling families that people don't normally think of as causal. So
that sounds super. Yeah, that sounds super exciting. Honestly, I can't wait to see that.
Yeah, I'll hold off on the other thing because I think we're going to talk about it later. But we've also been able to extend ChiRho to support what's called efficient estimation. So now, with more or less the click of a button, ChiRho provides efficient estimators for more or less any probabilistic program and any query you write in ChiRho, which is very exciting.
Okay. Yeah, I mean, we can talk about that now. That sounds interesting. So yeah, maybe define what you mean by efficient estimators, why that's useful, and in which cases, like why would people use that concretely?
Yeah. Okay. So when solving causal inference problems, you inevitably have to solve some estimation task, right? So if I'm interested in the effect of some treatment on some outcome, and there are confounders, I need to adjust for all of the potential confounders that I'm observing. One way of doing that is to build a regression model of the outcome given all the other things. So essentially, fit a some distribution P of y given this huge vector of covariates and one individual treatment. And without even going Bayesian, even just from a frequentist perspective, you can show that as the number of covariates gets very, very large, even though you're only trying to estimate a single treatment outcome relationship, your error rate, like the ability to get closer and closer to the truth, doesn't decay that fast. Essentially, you have what are called a lot of these nuisance parameters, a lot of parameters that are necessary to fit the model that don't really matter for the question you're trying to answer, that you'd like to kind of ignore, right? You can think of it as a kind of like statistical budgeting, right? I've got a finite amount of data. I want to allocate the statistical juice I get out of that data towards the questions I care about and not all these other nuisances that don't really matter. So an efficient estimator is an estimator that behaves as if you were only estimating a single variable in this regression, a single parameter.
Okay.
So it gets it approaches the truth as fast as if it were just a 1D regression problem, with some constants thrown in. But that's the general idea.
Okay. Yeah. So it's gonna make like ideally this is something that users wouldn't even really need to be conscious about. Right. That's something that ChiRho would do under the hood for them, so that it's much faster to have their analysis run. But like the normal user wouldn't even need to worry about that. Am I right?
Yeah, that's right. So right now it's quite computationally intensive. So we leave it as a separate module that you can either use or not use. But yeah, that's the general idea, is that systems like ChiRho should automate the hard math of finding these efficient estimators.
Yeah.
So that you can focus on modeling and asking questions, and you don't need to have a PhD and a lot of expertise in functional analysis, for example.
Yeah, that makes sense. That's also the what we try to always optimize for in PyMC, for instance. And so it makes sense that you guys are doing the same thing. Do you have anything to add on that, or should we try and go through a concrete do operator example for listeners to make sure the idea clicks?
Maybe I'll add like a little bit of detail for the really interested listener. So the way that algorithm works is there's a paper led by Raj Agrawal, which is a spotlight at NeurIPS last year, where we show how to estimate what's called an efficient influence function. And maybe all I'll say is that there's been a lot of literature in the semi-parametric statistics literature that shows that if you were able to find an efficient influence function, you can get these efficient estimators for free. There are a number of general recipes for using this efficient influence function object to build efficient estimators. The challenge before our paper was that finding an efficient influence function required a lot of handcrafted math. And what our paper shows is how to approximate the efficient influence function using only quantities that an ordinary probabilistic programming system can give you. You need derivatives of probability densities. You need to approximate the inverse Fisher information matrix. But that's something you can do using an AD system and a probabilistic programming system. So we show in the paper that using this technique, even though it's an approximation, you get arbitrarily close to the what the efficient estimators would be. There's a number of experiments. Check out the paper for the cool math.
And make sure to add the paper in the show notes if that's not done already, because I'm sure interested listeners will go and check that out. Cool. Do you want to go through a do operator example now?
Sure. Yeah, sounds great.
Fantastic. Do you want to share your screen again, or do you want to do that?
I don't have a visual explanation. I was hoping we could just talk about it, but
No, that works. So I was just curious how you wanted to do that.
Well, sure. Yeah. Okay, so maybe this isn't what you were looking for, but I think you can think of a do operator as modeling a kind of uh, thought experiment where you force something to be true or not true, or a particular value. So you could imagine a model relating medication that patients take um, and their health outcomes and some variables describing their behavior, right? And in your original model, all of these things are connected. The, the, the way people behave in the world, their diet, their exercise, may causally influence the medications they take, and may also causally influence their health outcomes. This is what we would call a confounding variable, as we said before. And if you want to ask the question, does this medication influence cardiovascular disease, for example, you can model that by instantiating a kind of thought experiment where you've forced some people either to take the medication or not take the medication, regardless of what their ordinary data generating mechanism would be. And that act of forcing someone to do something is modeled in ChiRho using this do operator. So the way you would do that mechanically is you write a probabilistic program describing the way people, the way you think people choose to take medication or not. And again, this can be kind of a statistical model or machine learning model with many free parameters you learn from data. That's all fine. And then in asking your question, what is the effect of medication on cardiovascular disease, you would instantiate two counterfactual worlds and intervene to set one world where the patients are forced not to take the disease, one world where the patients are forced to take the disease, and then compute their difference in outcomes. To see this concretely in code, maybe I'll share after some specific pointers to ChiRho's documentation where you can kind of walk through similar examples where the actual syntax for the do operator is being used.
Yeah, for sure. I mean, I've looked into those before the show. Also, for people who've listened to Robert Ness episode here, well, I recommend to go through it. And if you have his book, also he goes into a lot of details about the do operator.
Yeah, it's good that you mentioned Robert. So it's a lot of the ideas I'm talking about, I like to try to be careful with credit assignment. So I'm not claiming that I invented any of the kind of general ideas of sort of causal probabilistic programming stuff. I think Robert, me, Alex Lev, Eli Bingham, Zena Tavares, and Jeremy Zucker all wrote this kind of opinion article maybe 4 or 5 years ago together, kind of outlining this general kind of approach to thinking about causality in probabilistic programming. So just quickly wanted to give credit where credit is due. And I know Robert pretty well, and we've chatted about a lot of these ideas for a long time.
Yeah. And I've added, so he was on episode 137 of the show, and it's in the show notes already, folks. So definitely recommend giving that a listen. That was his second appearance, actually, on the show. Maybe a more general question for you about ChiRho, Sam, that I have is, what would you say are the best use cases for it, and when would you recommend listeners to give it a go?
So I think it's quite a general purpose tool. If you're interested in kind of purely statistical forward causal inference workflows, you can represent a lot of common assumptions as probabilistic programs in ChiRho. And we have a number of tutorials that show how to do that. For example, we have a synthetic difference in differences tutorial for causal inference in panel data. We've got some models about proxy variables where you have a latent confounder and some measured proxy of that confounder. So a lot of the kind of core kind of statistical, econometric, social science models and assumptions can be pretty easily represented in ChiRho. What I'm most excited about are these kind of hybrid models where part of your model is like physical equations, like I said before, like mechanistic models, and part of the model is kind of filled in with machine learning that where you may assume a causal structure, but you don't know much about the particular functions relating variables, and you just kind of hot swap in a machine learning component in your probabilistic program to represent that kind of broad uncertainty. So I think either of those two camps would get a lot of value out of ChiRho. It's also worth mentioning that like ChiRho provides some interesting capabilities, even if you don't have data and you just want to probe your model. So asking these kind of mediation analysis questions or attribution questions, even just from a probabilistic program you write from hand, can be really insightful. It can tell you a lot about what the implicit assumptions you're making about your model are. It's nice that it happens to work well with conditioning on data and then doing posterior inference over parameters.
Yeah, yeah, exactly. I mean, it's also something that you get from Bayesian modeling, right, where you have to explicit your priors and your structure of the model. Then, if you add the causal structure on top of that, it also makes your modeling assumptions even clearer, and you get to know whether you can actually answer the queries you're actually curious about, or if you need to refine your graph, your causal graph, or if you need to refine your data if you can.
Yeah. Yeah, it's a great point. So I think another audience who might get a lot of value out of looking at ChiRho are data scientists who are familiar with Bayesian modeling, but maybe less familiar with causal inference. Because I happen to think that this view of causal inference as writing probabilistic programs and then transforming them is fairly intuitive for people who are already used to writing probabilistic programs. And to me, it makes the assumptions seem much more clear. Often the causal inference literature can be very verbose and complicated. And I've always found it much more clear to look at a program and to kind of try to tease apart what assumptions are being made in that program.
Yeah, completely agree. I'm the same. I'm also a very practical and visual learner. So looking at the code and the programs and playing with it is actually a much better way for me to learn. I also get lost in the terminology, you know.
Yeah,
right. Like actually seeing what the different objects represent is much more efficient for me.
Yeah, it's also unfortunate that there's so much terminology because
right.
The ideas are so universal, and these different camps actually are quite intimately connected. I mean, you can translate between them. If you know the language, you can translate between them. But from someone who's just getting into causal inference and looking at this kind of literature, it's very confusing, unfortunately.
Yeah, for sure. That's why I also have these podcasts and trying to be a bit helping people about let's like out of the terminology, what are we talking about here, and how can we actually use that on real models and use cases.
Yeah, I think it's great that you're talking to people and kind of cutting through the jargon and the papers and the software. So I find just, like I said, talking or just listening to people talk, it's very clarifying.
Yeah, exactly. And that's also why I keep doing this show. That like personally, I learn a lot by talking to people like you. So and that also makes the papers more, incarnated. Whereas reading a paper can be very cold. So
yeah, it's sort of unfortunate that in an academic setting you write papers almost defensively to prevent other reviewers from penalizing you too hard. But that trend, I think, pushes papers to be less accessible for people who would actually get value out of them. So now that I'm, out of my PhD a few years now, I'm sort of inclined to just like write blog posts. It seems a bit nicer than I'm still writing some papers, but it's not as obviously the best communication medium to me anymore.
Yeah, I completely agree with you, and yeah, I'm I always say that I read papers because I have to, but not because I want to. It's like, yeah, reading papers is never fun, honestly, for me. Reading blog posts, reading package documentations as you have on ChiRho, reading books, like Robert's books, or, like, this is much, much more entertaining to me. Also because I think here what you're trying to optimize is not whether you're going to pass the threshold for peer-reviewed publication, but it's mainly just, well, I want people to enjoy what they are going to read and remember what they're going to read and be interested in it. And so that's a much better function to optimize than the first one.
Yeah, and ultimately, if I want these tools to be useful to people, you have to have people use them and have it be a pleasure to use and understand. As you know, yeah.
That's a good point.
I will say, when I'm learning a new field or a new subfield, I actually like to read PhD dissertations. I find that when you write a thesis, you have to write all this background and scaffolding if you do a good job, and that provides a lot of context, which is hard to find out otherwise.
Yeah, I see what you mean. Yeah, a thesis is almost like a book, right? I think it's basically the same. Could be a book most of the time. So
right, that's true.
That helps.
Yeah.
And well, actually, I'm curious. Talking about ChiRho, what do you have in mind on the roadmap for the coming month? Is there anything you are especially looking forward to adding, to making better? Do you need any help on that? The links are in the show notes, so people interested in making some PRs for that, they can look into that. Yeah, what's the state of ChiRho?
Yeah, so me personally, I'm doing a little bit less core development work now that I've picked up more of this consulting work. But there are some things I'm excited about. So one is extending some of the dynamical systems work I had talked about before. The landscape of dynamical systems models is very broad. So far we've gotten support for ordinary differential equations, but you might also want to model stochastic differential equations, differential algebraic equations, PDEs, those sorts of things. And that's going to take a lot of development work. As far as how people can get involved, ChiRho, we try to maintain the issues and pull requests as best you can. And if you browse the issues and see any tagged help wanted, just jump right in, or discussion, anything like that. It's totally open source. We welcome pull requests from the community. Just ask that you write tests and engage in conversation. Yeah,
well, that sounds great. So, folks, if you wanna get in there, please do. And and I'm sure you will be received very well.
One thing that's always useful for a system like ChiRho is more examples. So we have a number of examples and tutorials, but we're really only scratching the surface of the kinds of things you can do with ChiRho. So if you think of interesting causal machine learning methods or models you want to implement and share with the world, that's a really good avenue to contribute to open source software. And I think it teaches a lot.
Yeah, it's also a lot how I learn about a new method, right? It's diving into an example, trying to find a use case, and then just trying it and see what doesn't work, what I didn't understand yet, and that really makes me understand way better than just passively consuming content. On the roadmap though, do you know if the other devs have something in particular they want to develop in the coming month, or is it pretty much open right now?
I think ChiRho is pretty open. So some context. ChiRho is built by a number of researchers at a nonprofit research institute that I used to be a research scientist at, named Basis. Constantly hiring great people, doing very interesting work. So ChiRho was developed as a part of Basis. Again, like I said, it's fully open source. And there are a number of other open source technologies that people at Basis are working on. I think the plan right now, I'd have to check in with some of the other ChiRho developers, but I think the plan right now is to kind of rebuild kind of the foundation of probabilistic programming systems from the ground up. So for now, don't take this with a grain of salt, but my understanding is that ChiRho is fairly stable, and that there are more kind of larger scale visions on the research pipeline there.
Yeah, I see. So actually, let's talk a bit about your Sorbus AI company, because now that's your main gig, as you were saying, and so
that's right.
Yeah, yep. I'm curious. Of course, I'm very curious about it, because this is what I used to do. This is I've been in the exact same place as you are right now with MCLS, but in 2020. So yeah, like, how is it going? What has been your biggest surprises? Granted, it's been only 3 months, you've told me, but I'm also wondering, what are the toughest real-world scientific question a client has thrown at you so far, and how did causal probabilistic programming help with it?
Yeah. So I can't say that much about what I'm working on, but from a high level, I have a few clients now who are in the kind of science and engineering or health space. So one is working on materials for sustainable energy products, and another is working on preemptive health. And both of these settings care about probability and causality, and machine learning and learning from data. So I've been able to kind of insert myself into their teams and support them in building models, understanding cause and effect relationships. And it's a lot of the work is translation. I think because causal probabilistic programming or causal inference is still a fairly niche topic, I'd say the largest challenge for me is not just jumping right out the door with a lot of jargon, and trying to meet people where they're at and do this kind of translation into causal and probabilistic assumptions in my own head. So it's fairly common that I'll sit down and meet with engineers and kind of in trying to probe causal questions for them, ask it in several different ways. Often the questions that I thought they wanted to ask were not exactly the questions they were asking. And actually, systems like ChiRho in those settings make it really, really easy to iterate on those workflows. So I can sit down with an engineer and say, okay, well, you have this kind of vague causal question you're interested about this domain. Here's one proposed way of codifying that concretely, looking at the implications together in the span of a few minutes, and then having them say, well, no, that's not quite what I wanted. Could we think about this other kind of causal question? And then with just a few lines of code, changing the question and getting answers right there in a live environment. That's turned out to be really powerful as kind of a modeling workflow. I think the biggest challenge, this is not specific to clients I have now, but the biggest challenge I see in like getting broader adoption out into the world is that for some reason it seems like people forget that when you have high dimensional data, correlation still does not equal causation. I don't know why that is. Like, I think that there's just this really strong tendency to anthropomorphize machine learning models to doing what they're not doing. Especially given all the kind of hype around agentic systems, LLMs, reasoning models, these kind of things. It's very tempting for everyone to kind of say, well, let's just throw AI at it without really knowing what that is or knowing what the implications are. And in trying to be rigorous and precise, that's kind of an uphill battle. You can find yourself battling. That said, I think my current clients, I'm very lucky to have collaborators who are careful, thoughtful, measured, maybe don't have as much expertise in the specific things that I'm offering, but in general are kind of critical enough of hype cycles that they're not just buying all into LLMs as a kind of one-stop shop for all your AI needs.
Yeah, that makes a ton of sense. I definitely resonate with that. And of course, I have delivery that's coming in, so I'll come back in like 5 minutes tops, and then we'll get back to that. Basically, I'll pick up on that and talk about what we were talking before recording. Where with like the adoption of causal inference and stuff like that. And
yeah, sounds great.
Then, yeah, awesome. I'll be back in just a few minutes.
See you soon. Sounds good.
Yeah, I actually have a similar experience, and something I was always very curious about is that you often have to justify that you want to take a causal path. And I'm always, surprised by that, because it was like, it feels like the burden of proof should be reversed. You should want, especially if you want scientific answers, you want reproducible results. So I'm always thinking, well, why would you not want causal results? Should be the default. But yeah, somehow it's not really. I have different speculations on why that is, but I'm curious what your experience and thoughts are on that.
Yeah. Do you want my hot take, or do you want my measured diplomatic response?
Both. I think both are going to be interesting.
I'll give you. I feel comfortable. Let's go with the hot take. So
yeah,
I think one of the major reasons why people are hesitant to go for causal inference is because there's a academic tradition of being almost curmudgeonly when people make causal claims. It's just because causal inference is hard, it's very easy to criticize. I mean, you need to make a number of assumptions, and the conclusions often depend strongly on the assumptions that you make, which is, it's good to know. I mean, it's worth being critical. But I think, unfortunately, what this means is that people often are so afraid of being criticized for overstepping in their causal claims that they don't even make an attempt in the first place, and instead use kind of causal-ish language with associational methods, but never actually go out there and say anything about causality because they're kind of afraid. So let me give you an example. Several years ago, I worked on a problem called genome-wide association studies, which is about trying to understand the association between single nucleotide polymorphisms, like the positions in your gene sequence, in your DNA, with various health outcomes. So if you have this single nucleotide polymorphism, you're more likely to, get, I don't know, cardiovascular disease before you're 60 years old, something like that, right? And if you look at a lot of the methods in genome-wide association studies, they look like causal inference methods. So you adjust for potential latent confounders. You even do this kind of latent PCA correction step that looks like some causal inference methods that have come out in the last several years on, it's called multi-cause confounding. But the methods are called association studies. Again, I think because it's very risky to say that a particular single nucleotide polymorphism is a cause for a particular phenotype. And it's good to be hesitant, I think. Again, the problem with that kind of cautious worldview, I think, is that you have to make decisions. And if you have to make decisions one way or another, implicitly you need to reason about causality. So if you're choosing to bury your head in the sand and say, I don't have strong enough assumptions, I'm unwilling to even make any sort of a causal claim, what you're implicitly choosing is to just do causal modeling poorly. So I think it is better to be honest about what you're trying to achieve And if you really care about causality, try to model the problem as a causal problem. And to the best of your ability, represent your uncertainty and your assumptions explicitly, and be cautious in how you interpret them, but still, go forward somehow. I like to say often, inaction is action. Time is passing by, right? And if you have a choice of making a policy or not making a policy, and you refuse to make causal claims, you're choosing not to make a policy.
Yeah, definitely. Yeah, the fact of not doing anything is already doing something. So you're choosing
exactly.
to stay with the current solution, actually. So
Yeah.
And I think this is definitely one of the big reasons. I also see kind of the same phenomenon at hand with Bayesian models generally, I would say, because they are much better at being poked at, right? Like you know when you have divergencies, when the sampling's not going well, you can check the priors, you can check how the posterior is contracting around how the prior is contracting around the posterior. You can test again the different test values and so on. So it's much easier to poke at a Bayesian model than it is to poke at a classic frequencies model, and so that means your assumptions are also much more out in the open, and so you have many more things to criticize much transparently. And so I can definitely see that being weirdly an impediment to putting in production better models that are more open, but
Right.
they are easier to criticize, so then it's easier to just delay them.
Yeah. There are some settings where you can get away with making fewer assumptions, and that's good. But as you're saying, sometimes you need to.
And I mean, in when you do causal modeling, you need to, like, even from a mathematical perspective, like the ladder of causal inference, the three levels that Judy Appel's demonstrated are not, just a way of thinking about things and just putting things in bucket. It's actually a mathematical derivation of what you can do with the data model and assumptions at hand. And if you're not willing to make level 3 assumptions, so counterfactual assumptions, then you will never be able to make counterfactual claims. And it's just
that's right.
like that, So it's not like we're saying, that's a cool thing. You can just divide things into categories. It's actually kind of it's a theory, So you have to make a choice.
So that's, if you don't mind me digressing a little bit, there is one caveat about the kind of Bayesian approach to causal inference that I'm proposing here that I want people to be aware of, which is that...
Yeah, go ahead. I mean, nerdy digressions it's the subtitle of this podcast, so you know.
Great. Okay, good. I'm in comfortable territory then. So zooming out a little bit, this Bayesian approach to causal inference and ChiRho's kind of mathematical underpinnings don't escape this fundamental need for assumptions that you've described, right? There's no free lunch in ChiRho. It doesn't magically mean that you can derive causal conclusions from nothing. ChiRho really should be thought of as a way of writing your assumptions and then seeing their conclusions. So the way identifiability shows up in this Bayesian framing is in the posterior itself. The idea is that if a query is not identifiable from the data, then the posterior distribution should never collapse to a single point or the truth, regardless of how much data you get. So that's I think a well-defined kind of mathematical framing of what identifiability is in a Bayesian setting. The tricky thing is that if you want to know whether your query is not identifiable or not, just running approximate inference turns out to be a pretty bad method. These kind of non-identified posteriors can get arbitrarily thin you can think of it as like a manifold in a higher dimensional space, and expecting any approximate inference algorithm to like fully traverse that manifold is asking too much. So I think what will often happen is that if you use an approximate inference algorithm, it'll find a mode of that kind of infinitely thin posterior and then get stuck there and imply that you have a lot more certainty in your answer than you actually do. So it is still worth doing the kind of explicit identifiability analysis beforehand, just to make sure that those kind of pathologies aren't misleading you in your causal conclusions. Now, in theory, if the probabilistic inference methods continue to get better and are able to traverse these like very challenging posterior landscapes, this will be a non-issue. But for now, it is an issue, and I wrote some work in my PhD about how to address this. I think it's kind of an incomplete. The paper I wrote is kind of incomplete, but people can read it if they're interested, and I'll share it in the show notes for one way of thinking about identifiability, or how to find whether causal questions are identifiable in this kind of Bayesian setting.
Yeah. Oh yeah, definitely. Yeah. Do share that. I'll be very interested in that too. Like I know the do-while library has a very good user interface to help people see if their causal queries are identified. But this is not in the Bayesian framework, so it's going to be very interesting to see.
Yeah. So I haven't looked at do-I in a while. I know a few of those guys quite well, and well, I know them okay, and I think highly of their work. My memory the last time I looked is that it's still very much in the kind of non-parametric graphical models setting. So some of the assumptions that you can represent in a system like ChiRho that end up being very practical are very difficult to reason about there. Things like the regression discontinuity design I described earlier.
Yeah. Okay, I need to place out here because I've already taken a lot of your time. So I had a question about your Gaussian process paper that you authored a few years ago. So maybe we'll go with that one because I'm very curious. I love GPs. I use them all the time. So when I saw a paper about Gaussian process and causal inference with structural latent confounders, I needed to ask you about that. So yeah.
Sure.
Can you tell us what this is about and how practical this is for people if they want to use that in their own models?
Yeah, sure. So that paper is several years old at this point. I think it was 2020 when I wrote that. I forget exactly.
Yeah, I think the release date is 2021. So knowing academia, you must have written it in 2020.
Yeah, which was, I guess, right. That was just when the COVID was starting. Which feels like an infinite amount of time ago now. So that paper was about combining two different ideas. One is using Bayesian non-parametric models, Gaussian processes, to do causal inference, and encoding a particular kind of assumption that we call structured latent confounding in the paper. And the idea behind structured latent confounding is that there are many, many settings where you have a kind of hierarchical structure between objects and units in your data. So for example, if I have data for different schools and different students that each belong to that school, there's a many-to-one relationship between schools and students, and there may be many different schools for which I gather data on students. So that's super, super useful in causal inference because you can make assumptions of the form any confounding variables, any latent confounding variables, if you can assume that they're at the level of the school and not at the level of the student. So for example, a school is in a particular geographic region, so all the students in that school are subject to the same geographic region, the same influence of that geographic region. So if you're willing to make that assumption, you can get a lot of, you can still estimate causal effects, even though you have this latent confounder, because of the structure you've assumed. One way of thinking about it is like, if I were to bundle students belonging to the same school and look at the difference in their outcomes under different treatment conditions, because they're all subject to the same school, that wouldn't be biased. So then if I want to aggregate a bunch of different schools together into a kind of holistic causal estimate, that intuition of being able to like isolate the effect of the confounding variable at the school level still holds as you get to multiple schools. So the paper is really somewhat mechanical. It's just showing how to combine these two ideas. So you have a Gaussian process regression for the outcome model and a Gaussian process latent variable model for modeling this latent confounder. And what we found empirically is that it seemed to do pretty well for effect estimation in these kind of hierarchical settings. Now, that specific model, I think there are a lot of things that could be improved. It would take a long time to talk about all of them. But I think the core idea of taking Bayesian nonparametric models and combining them with these kind of richly structured assumptions is a very powerful one. And that general idea I've used in, for example, time series modeling or other kind of hierarchical or relational models, maybe not specifically with Gaussian processes, maybe with, I don't know, some normalizing flow neural network or something else, and it seems to work very well. So I think that the essence of that paper, I think, is generally useful, even if the specific model is not as compelling. There's also a little, like if you really want to nerd out in the supplementary materials, there's some technical detail about how to reason about what are called individual treatment effects with Gaussian processes. The subtlety there is that when you're sampling from a GP, you don't have access to the structural function directly. You kind of only have access to the marginal distribution of data integrating out the structural functions. So you can't do the kind of default thing of like passing in an argument and holding the noise fixed. So there are some tricks in the paper for how to handle that.
Okay. It's cool, yeah. How did you guys implement that at the time? Were you using ChiRho again?
No, so at the time I was a visiting student at Vikash Mansinka's lab at MIT. Vikash's group produced a probabilistic programming system called GEN, which is written in Julia. That was led by Marco Cusimano Tanner. He's also a really sharp guy, great friend. So at the time I was doing all my research work in that probabilistic programming language. It has a lot of the same kind of ideas as ChiRho. I mean, a lot of these probabilistic programming systems look very similar with some different emphasis on their design. So there, it took me a long time to write the models because I didn't have a system like ChiRho at the time. I was like manually building out these counterfactual worlds in just a single program by hand.
Yeah, that's hard.
Which is hard. Yeah.
Yeah. Takes time. Okay, yeah, this is super cool. So as usual, the paper is in the show notes, folks. If you're curious. Sam, before asking you the last two questions, I'm also curious, in general, where do you see the field you're in? So, like everything we've talked about right now, basically intersection of probabilistic programming and causal inference, where do you see that field going in the next few months? And also if you have any advice for people interested in joining this field.
Yeah, so I mean, it would be a little sad if I said the thing I'm most excited about is not the thing I'm going to be working on. So with that caveat in mind, I'm very excited about this kind of engineering and science-focused probabilistic programming workflow, right? Like the kind of models I'm really enthusiastic about are the models that combine kind of physical laws with statistics or machine learning forward models. And there are a number of different ways to combine these two different modeling paradigms. I think I'm pretty optimistic that these kind of probabilistic programming tools will lead to actual real discoveries, like actually make science faster, more generalizable, make it easier for people to communicate with each other. I think, we should have a bold vision of where we want to kind of bring scientific computing. And I see these tools as a really fruitful path to go to like a new era of scientific computing. As far as how to get involved, my recommendation for anyone at a kind of high level is to touch software, get into the implementation, submit pull requests, even just submitting issues, writing up examples. I think it's really, really instructive to write code. And it's also a great way to get a built-in community. People are much more likely to listen to you and engage with you if you have a conversation attached to a pull request that contributes to their software. I think from an academic perspective, I am seeing more and more academic communities being open to this idea, both in science and engineering, causal inference, and machine learning. I think people are excited, so it's a good time to write papers about these ideas. In fact, one way of thinking about ChiRho is it's kind of a paper factory. Write a model in ChiRho, spend a month doing it, write a paper, add to your H-index if that's the game you're in. It's a little tongue-in-cheek, but I'm also sort of serious.
Yeah, that makes sense. Yeah, and I agree with that. That's also a way for you to, if you're starting out, to get really good mentors who are going to have your best interest at mind because, well, you are also contributing to something they really care about. So, it's a win-win.
Yeah, and specifically, if people are interested in the specific work that I've done, feel free to email me. I like to make time to just talk to people about their research interests, even if I get nothing out of it. I might say no, but it doesn't hurt to shoot an email.
Yeah. Careful though, because millions of listeners. So I've heard
That's true.
Former guests who can't leave their house now because people are just outside all the time asking for selfies
have a very
and autographs. So yeah.
I have a very comfortable couch, so that's okay.
Awesome, Sam. Well, that was really great. As you can see from the document I shared with you, I still had a lot of questions, but I need to be respectful of all your time. So let's call it a show. And of course, let's ask you the last two questions I ask everybody at the end of the show. So first one is, if you had unlimited time and resources, which problem would you try to solve?
Yeah, I think that's fairly easy for me. I want to solve our environmental problems. Like I'm motivated by the kind of core technological and policy questions behind climate change, but also beyond climate change. I think things like just general pollution or waste disposal or energy scarcity are really important problems, and I think it's going to take technology and policy. And I'm hopeful that computational tools like those that I've worked on will help make that happen. In a certain sense, I see one of the core problems as getting people to collaborate. I think that's a really interesting kind of computational problem, and I'm hopeful that probabilistic programming technology could help there. It's not exactly clear what that looks like, but if I was starting a PhD right now, that's what I would work on. Yeah,
love that. And second question, if you could have dinner with any great scientific mind, dead, alive, or fictional, who would it be?
I'd have to say Isaac Newton, which may be kind of a stereotyped answer, but I think there's something about his discoveries that seemed very transformational, like a paradigm shift. And I'm very curious about what leads to kind of non-incremental progress in scientific thinking. I think sometimes, we need to take big steps, and he was one of the kind of most obvious big step scientific thinkers that I know of.
Yeah, that's, to say the least, for sure.
Yeah. Although I hear he was a weird guy, so maybe he wouldn't be very pleasant to get dinner with.
Yeah, I don't know about that, but I'll be curious when that happens. You let me know, please. I'll be happy to join the dinner. Yeah.
Yeah, you're invited.
Awesome, Sam. Well, that was really fantastic to have you on the show. Please come back anytime you have something new in the world of probabilistic causal inference. The show notes are going to be full for this one again, folks, so do give it a look if you want to dig deeper. And Sam, thanks again for taking the time and being on this show.
Yeah, thank you very much for having me and doing what you do.
This has been another episode of Learning Bayesian Statistics. Be sure to rate, review, and follow the show on your favorite podcatcher, and visit learnbayesstats.com for more resources about today's topics, as well as access to more episodes to help you reach true Bayesian state of mind. That's learnbayesstats.com. Our theme music is Good Bayesian by Baba Brinkman, feat. MC Loss and Megaran. Check out his awesome work at bababrinkman.com. I'm your host, Alex Andorra. You can follow me on Twitter at Alex_Andorra, like the country. You can support the show and unlock exclusive benefits by visiting patreon.com/learnbayesstats. Thank you so much for listening and for your support. You're truly a
good Bayesian. Change your predictions after taking information in. And if you're thinking I'll be less than amazing, let's adjust those expectations. Let me show you how to be a good Bayesian. Change calculations after taking fresh data in. Those predictions that your brain is making, let's get them on a solid foundation.